Okay, so what is Numba? Numba is it's actually a package that have a special compiler for accelerating numerical focus operations. Okay, so let's define four advantages. So first is it's function compiler that Numba compiles Python functions and actually can accelerate parts of the program. Okay, so if you have some parts of your programs that actually have need a lot of computations, you can accelerate it specifically by using this library.
Does it use C?
No, it doesn't use. Okay, so actually, it's use NVCC. It's GPU. It's CUDA C. It's a GPU language. Okay, so it's This compiler is compiled from Python to CUDA C. And then it's compiled to assembly, and then it's run.
So it's only relevant for Python. It won't be relevant for.
Why?
Because TensorFlow compiles your Python code into a C code, a real C code, and then compile the C code to the GPU.
No, it's actually you have in your in TensorFlow you have a Cuda 2. Okay, so you so Cuda it's CUDA library. So it should compile to it should compile through NVCC.
Right, but between the Python interface and this interface, you have the TensorFlow, which compiles it to a C and then moves it.
Yeah.
Maybe I'm wrong. This is what I know about TensorFlow, but PyTorch is definitely.
Yeah. Again, I'm not big expert on TensorFlow. I'm talking about I know how it works on PyTorch, and you will see example of adding it in next tutorial. We'll see actually a code our special kernel that we integrate to our PyTorch. It will be special dedicated kernel coded by CUDA and integrated to your PyTorch for accelerating some task, some part of your algorithm. Okay, so let's continue. The next week I will talk about more what kind of operations should be accelerated in the PyTorch and what actually have a good acceleration itself by using the special libraries like Cuda. You all of you used actually when you accelerated your code on GPU on your using PyTorch. You already have some optimizations, okay, that have done there. But if you do some custom work, some custom neural networks, and you do some pre-processing, some stuff that are not the part of your graph, then you want to accelerate these operations. And here you can use some kernel, some dedicated kernel that written in CUDA. Okay, so this is why we are talking about CUDA. Why we need CUDA. Great. So let's start. So we talked about function compiler. So we have type specialization. So Numba speeds up your function by generating a special implementation that optimize specifically this operation. It works just in time, so Numba translates the function where they're first called, and then actually for when you first coded them, so you have your compiler is build for them the code. Okay, great. So and it's very easy to use it in Jupyter Notebook and other it's easy to integrate it to other Python frameworks. Okay, so and Numba is focused on various of numerical data types, including integer, floating point, and even complex numbers. Okay, so most of the neural networks are not complex, have not complex number, but again, you can integer and float. It's very, it's actually it's most of the neural networks have both of these operations, hybrid custom operations, and we will, when I will give you a lecture on quantization, you will understand why actually, how we do it, how we convert from floating to integer, and what the reason to do it. I will have give your scoop today about if you reduce the number of the representation, it costs less power. Okay, so it's one of the reasons. Great. So first steps. So let's see the example. So first function is actually we want to measure hypotenuse. אני מקווה יתר, okay? So hypotenuse, I think so. So actually, yeah, I gave a credit to implementation from Wikipedia, but I think it's so. Yeah, so we want to measure our hypotenuse. So I defined our x and y, and I want to return the screw error of the their number of their summing. Okay, so the first time we call our function hypot, the compiler is triggered and compiles a machine code to float inputs. Okay, and Numba also saved the original Python implementation of the function in the py function attribute. Okay, so let's measure. Let's do some measuring. So it's hypot. We feed 3 and 4, and the answer is obviously 5. So let's measure the speed of the origin Python version. So it takes 4,000 nanoseconds, okay? And we use some time measuring function, time it, okay? Great. So then the best three approaches also ensure that the compilation time in the first of the first call doesn't skew the results. So when we do few iteration, it's actually take less time. Yeah. So Numba did a pretty good job with this function because the first of it we use Python implementation. The second was Numba implementation. Okay. So of course the type of function is already presented in Python module. So here I do more iteration, and Python build and now it takes 77 nanoseconds. Okay, so Python builds in ever faster than Numba. Why? So now we have a question why. This is because Numba does yeah, sure. This is better? Yeah. Great. So Python built. Okay, so we measured this function with Python and with Numba. Okay, so and now we see that Python built-in is ever faster than Numba. So this is because it's happened because we have some overhead to each function to call it larger than the function actually executed. So it's actually one of the biggest reason when we want to understand which part of we want to accelerate. So we need to take an assumption. We need to take in our assumption that calling function takes times. So you want to accelerate some if you have some program. some programs that have some actually it's overall. So you want to accelerate big parts of this program, okay? Because if we are taking some small program or set program, so calling function that actually optimize specifically for this task, it takes time. So you have no advantage on this. The communication time. So you have computation time and communication time. Computation time is it's actually the time that it's proper taking the calculation due, and the communication time is that yeah.
You said about the Numba that, for example, pre-processing, if we have a long routine,
Yeah.
when we do all sort of calculation using NumPy,
Yeah.
we just need to put the decorator for Numba on top of the function, and basically this is it? Or should we parse it and decorate smaller function inside the big routine?
You're talking about how.
Use Numba for a big function.
Okay. First, you prefer to do big. You want to accelerate big arrays. So you don't want to derive it. You don't want to derive it to the small sub-functions, because we will talk about in a few minutes. We'll talk about GPU. So the way that GPU accelerate, it's very important to understand it, because GPU is working in SIMD mode. SIMD mode, he accelerates single instruction on multiple data. So your advantage could happen when you take in very large arrays and accelerate them in a given step. So you want to take bigger. You want to do biggest multiplication or operation that you can. Okay. Making smaller operations, we will see here in a few minutes. You have no advantage, because CPU do it faster than rather GPU. Okay, so one of the curious problems is accelerating small matrix operation. It's actually CPU. It's working, doing it better rather than GPU, because it's actually you have no benefit of because the CPU clock it's faster than GPU clock, and yeah.
What's the definition of big?
Big. Okay, very good. You're asking good questions. So, when we do matrix multiplications, empirically justification of using GPUs, it's matrices from 200s, 300s. Bigger than this number, it's big enough to have advantage. Small, it's 1,000 and less, 100 and less, 100 and less. Okay. More than 200, 300, 200 by 200, yeah, 200 elements. Vectors that have 200 elements. And in deep learning, why GPU is you have a big acceleration in GPU, because why in deep learning you have acceleration using GPU, because in deep learning you multiply huge matrix in this term, okay? So you have very, very big matrix. So thousands and more, yeah? This is one of the benefits of why GPU is now best accelerator for GPU's training. Great, guys. So let's continue. Great. So now we talked about Numba. Numba, it's a function that you already have there, optimization using on CUDA level, okay? But what happened when you have the accelerations that you got is not enough, okay? So you want to actually programming one level lower than Numba. It's actually a level of CUDA, okay? So CUDA is actually the prime language of GPU, okay? From CUDA, it's you translate your code directly using NVCC compiler to GPU. So let's start introduce how the CUDA is integrated in Numba or in Python itself, and how we can add custom CUDA Python kernels in our code. Okay, so first we have U functions or GU functions. It's subject of this is actually we will talk about it, and CUDA Python kernels. Okay, so we will not go into CUDA hardware too much in this tutorial, but what we actually important that we want to remember that the hardware is designed for data parallelism. So what I talked about before. So GPU, it's data parallelism. It's not instruction parallelism. It's parallelism. It's actually you're taking a lot of arrays, and you can do the multiplication, your operation in parallel. Okay, but you do the same instruction. You cannot derive. You cannot do values of instructions for the same data. It's not dedicated. It's not good. It's not how GPU works. Okay, so universal functions are naturally data parallel, so we will begin with them. Okay, so universal function so that we have now. So NumPy has the concept of universal function, U function, which are functions that can take NumPy arrays of some variables and to operate on them element wise. Okay, element by element. So it's probably easy to show what happens by this example. Let's talk about example of adding arrays. So we have two arrays. We want to add them. So we can use U function. So there it's actually our naive way. So U function also can combine scalar with arrays. So you can add some scalar A with scalar 100 with array, and then we have it's actually immediate add, yeah, like we talked in logic design. So let's see. So here we have some C variable, and we can reshape it and add it, making some vector operation. So in above this what we said before, the B array is added to each row of C. Okay, so if we want to add B to each column, we need to transpose it. Yeah, it's what we do in matrix multiplication. So there are several ways to do it. Okay, but one of our ways to insert a new access using NP new access. So it's one of the ways to do this. So we create B column by this way. So we take our all the column, and then we define NP new access, and here we have array. Okay, so here we have our array. So and then we add NP add. We add actually our B call to our C. Okay, great. So this way we adding our two vectors. So Numba has the ability to create compiled function, or we actually can implement a scalar function of all the types. Okay, actually by broadcasting rules. Okay, so we will generate our CUDA requires explicit type signature and settings target attribute. So here we import from Numba attributes that its name is vectorize. So vectorize have inputs of we actually define int 64, all of inputs and outputs will be in representations of precision int 64, and our target will be use CUDA. Okay, so and here we will actually to add him. We will add these functions. We will add x and y, and we can print it. So a lot of things just happened. It's automatically compiled to CUDA kernel that execute U function in parallel over each element. Okay, so it's first we allocate our GPU memory to the okay. We will talk about how it's using GPU. You need first to take your data to transfer it to GPU memory, okay, and then you can calculate. Okay, so you should save your data on GPU side. Avi, I think, talked about it before. Yeah, great. So then we copy the input to the GPU, and then we execution make our CUDA kernel with correct kernel dimension for the input size. We should define it, and we will copy our result from GPU side to CPU side once we have completed making a computation of our kernel. And then we return it to the host. So host is our CPU and device is our GPU side. Okay, few revision. So let's take a look on some curious results. So using NumPy on CPU, this operation takes 800 nanoseconds. On the other hand, on using Numba on GPU, this operation takes 500, almost 600 microseconds. So, what do you think about the results? Not good. Yeah, definitely. Definitely, when you want to accelerate your computation, it's not what you expected. Yeah? So it was not. So, but when we started actually before the talk, we started that we need. What?
You have different amount of loops. You have 600.
Yeah, but it's averaging. It's okay. Why? You have the same. You have seven rounds.
7 rounds, but in the upper one, it did 1 million loops, and in the lower one, 1,000 loops because it vectorized your operation.
Yeah.
So you have 1,000 by 600 as opposed to 1 million by 800. So the Numba is 3 orders of magnitude better.
You're talking about Numba on GPU.
Yeah. Missing something.
But it's 3 orders of magnitude slower.
Yeah. Yeah. It's yeah. So Alex is right. So even if you take okay, you're right. But if you will take, it's actually if you will it's if you're taking the same number of loops, it will be the same order. Yeah. It's nanoseconds versus microseconds.
It's micro.
Yeah, I'm sorry.
Sorry, I didn't see it.
Okay.
I thought it was nano in the lower one as well. Okay.
Now you see it?
Yeah, now it's.
Okay, so now actually we have the same order.
Yeah, it's the same order.
It's the same order for magnitude. Of both of the operations have the same. So again, it's
Not what you expect.
not what we expected. Why?
Expected to be much faster in GPU.
No. Why? Yeah, of course. No.
With a small metric.
Yeah. So the reason that what we actually talked before that not all tasks and not all matrices could be accelerated using GPU, because when we're talking about when we take small operations, the communication, the time that actually execute. So you have two reasons. First reason, for using GPU, you need to transfer your data to GPU. It's taking time. The second is when you have a small amount of operations, CPU clock is faster than GPU clock. Okay, so actually the advantage of using GPU is because of its parallelism of taking hundreds or thousands of parallel operations that you cannot do in CPU. Yeah.
Does the number on CPU use multithreading or not?
Yeah. Of course, but you know, multi-threaded. So your modern CPU have 32 threads or 64 threads, or even if you take some very expensive CPU, it have 96 threads. Yeah, so and GPU can do 2,000 operations in the same clock. Great. Okay, so now we understand that when we want to accelerate using CUDA, we need to understand what we want to accelerate, and we prefer to accelerate actually big variable operations. It consists a lot of data. Great. So, sorry. Okay.
So you just add an annotation to call the interrupter that it's CUDA.
Yeah.
What's the difference between the two?
CPU? Yeah, I'm only noticed that the device that will compile it, it will be CUDA device, and that means that it will call automatically GPU kernel. Great. So now we will compute more. So we want to evaluate the Gaussian million times. Okay. So we have some function that we did it in implements some Gaussian function. So let's see. First we did it for a simple using NumPy. Okay, so you can see the times what 30 milliseconds, and then using use the GPU, and it was 3 milliseconds. Okay, so here, okay, again I will, okay, so you have now when we have bigger data bigger datasets that we want to compile it. So for CPU, you have advantage using GPU. It's take less time. Okay. Again, this is times that I measured. This is actually my times. So I have a very old GPU. So in the modern GPU, it takes you have more advantage. Okay, but still here you can see that you have advantage using GPU. So it takes less time. Yeah, great. So before that, I showed you the example that used int64. So guys, let's talk a little bit about representations. So when the data types in modern GPUs, you have other for each representation you have their speed up optimization. So actually operations between int64 are not optimized in GPU. Okay, or float 64, because you do not need actually using in deep learning tasks. You are not using you don't need this precision. Why you should use when you want to use precision of 64 is actually double precision. It's actually in some problem in problems that have some mechanics or heat transfer problems. Yeah. But when most of the neural networks are working on prediction, for actually classification and most of the regression problems, these data types are not. It's too much for the represent our result. So this is actually why most of the GPUs have very bad speed up results. Speed up computation on double precision, and better for floating point 32. And if you're going down, you have more and more optimizations. So for even now for health precision or float 16, it's more optimized in GPU. It's take less time. So it's very important what data type you're working on. Okay, great. So now let's see CUDA device function. So okay, I will. Okay, so your functions are very good. They can speed up your optimizations, but you can create also your custom kernel that you want to optimize some problems that have no that have not optimized with these U functions. Okay, so this is actually very easy to do it. You can use Numba CUDA JIT decorator. So this decorator is give you the option to write proper CUDA code, but it's not CUDA C, it's CUDA Python. Okay, so you actually have the same. You define your function as you defined before, but you have some intrinsics, special intrinsics that it's actually CUDA. Okay, but you do not. It's before that we used CUDA C, and it's actually it's very hard to integrate it in Python frameworks. So now there's no need to do it. All our CUDA kernels will be implemented in Python. Okay.
Do you mean the swig?
I'm talking about threads. I'm talking about We will now we talk about. But I'm talking about when we want to optimize manually. Okay. Again, we can use U functions that have their optimizations to CUDA. But if you want to create your custom kernel that will make your custom optimization, you should use CUDA, and you can use CUDA on with Python and not using C. Okay, so now we will see Numba have a extension to use CUDA to create custom kernel, of course. Okay, great. So now we actually we define our CUDA JIT. Okay, so device true, it means that it's going to execute on GPU. So we actually have some. This is first we see Python. It's our Python implementation. So it's actually using CUDA JIT. Okay, the second is actually we use vectorize using U functions. Okay, so we want to do polar distance, okay, and we define some polar distance, some thetas. So, and then we have some results. Great. So let's take a note that CUDA compiler aggressively inlines our device functions. So in general, there are no overhead for function calls. Okay. So it's actually you're doing on the fly. Okay. So it's not actually created as a Python object, but it represented temporarily as some structure. Structs that each struct have his own optimization. Okay. So let's talk about how we can use Python on GPU. Okay, so compared to if we compare Numba on CPU, which is already limited, because it's a new library. So Numba on GPU has more limitations. Okay, so what is actually the limitation? The biggest limitation of massively parallel programming is loops and conditions. Okay, it's one of the biggest. You cannot. Okay, before that, the era of deep learning. So deep learning is like non-condition, a lot of non-condition operations. So before this era, people wanted to accelerate a lot of general tasks, and one of the bottlenecks it's accelerating code that have conditions. Because conditions, it's actually you need to wait until you need to wait until the previous operations is ended. It's like branch prediction, yeah. And branch prediction, it's there are no branch prediction in GPU because if you add branch prediction to GPU, you actually you destroyed all of the benefits using GPUs. Yeah. Some questions? Okay. So if, else, and while and loops. This is actually this is the function that we want to avoid to accelerate, and it will be actually when we have this in our code, it's actually our synchronizations barriers. So we need to wait until until we end the operation, and then we can continue. Okay, so let's. Okay, so I have no. Let's talk about memory management. I will do it really briefly. We want. So first, let's see. So we have some function vectorize. Okay. So and then we have floating x and y. Our floating point, okay. So here we have some n 10,000. We want to. It's actually we want to plusing these vectors, okay. So baseline performance with host arrays. It's when we use host arrays, okay. It's like you're using your that the memory that the data is. On CPU side, it takes it takes 800 microseconds, okay, and then the Numba.Cuda model include the functions that will copy our host data to GPU and return a CUDA device return a CUDA device array. So first we use the function CUDA.toDeviceX. So it's taking our data X, deliver it to GPU. Taking y, deliver it to GPU. Then actually we can see it here, so we can print it and we can see their shape. So let's see. So it's when we print it, we see that it's Numba CUDA.CUDA DRV CUDA. It's actually object that this object is on CUDA side. So it's not in your memory, or not on global, not on DDR, or not on your CPU memory. It's on your GPU memory. Okay, once in the GPU memory, now you can use it and to make the operations that you need. So you can transfer between GPU and CPU side. So device array can be passed to CUDA functions just like NumPy arrays, but without the copy of overhead overheading. Okay, so you directly can transfer it without some overheading. So and here when we use it with optimize with these functions, you actually have speed up in your performance. So the big performance improvement already, but it was still allocated device array for the outputs using our U functions and copied it back to the host. We can create out buffer with NumPy device array, and then we can actually to compute it directly on our device. So here we have not initialized the context like in So again, so let's define what we did. We have a few options to make operations on GPU. First of it is using transfer, taking our variable that was on CPU, on DDR, transfer it to GPU, then making the computation, then to transfer it back to CPU for the further using. But you have, but we have here function of in Numba that do it on the place. Okay, so it's actually optimized. It's save our time from transfer from GPU to CPU because it's optimized. So it has some optimization functions that can do it without a big communication loss. Okay, so this name is unified memory, but again, it's not our scope. Okay, so it's some optimization functions that can save the time that the data is transferred from GPU to CPU side. Okay, so and here we can see actually the speed up of our performance. Great. So how we can write CUDA kernels? So actually we have you have a few guidelines that you can see. You can actually have more details, but let's actually focus on how GPU works. So GPU works. Okay, so GPU have structure. The basic structure is grid. Okay, grid have a lot of blocks. Okay, and blocks have a lot of threads. Each thread can compute one operation. Okay, so when we going deep into one block have some two-dimensional structure that have for more GPU actually it has 1,000 threads. So one block consists of 1,024 threads. Okay, so and then all your GPU have a lot of blocks. Each of block have threads. Each thread can compute one operation. Okay.
Is it the same operation for all the grid?
Yeah, all these threads compute same operation, but for each block. So if you have matrix multiplication, so or you want to add vector to vector, so you're taking first element with first element. So each of thread taking this operation. Okay, thread number 1, I'm making operation. I'm adding element of index 1 to element of index 1, and etc. etc. Okay.
The operation is it per block or per grid? Is it per block or per
grid? Okay, grid is actually all your threads in your GPU. So the number of CPUs the number of threads that are actually it's like active threads that you have on your GPU. It's actually the number of computational that you can do in one period. Okay, so you cannot, if you have a few thousands of active CUDA cores, it means that you can do in parallel 2,000 operations. Okay,
So
each of them are taking one element and execute it.
So why to divide it in blocks if also the grid?
Very good question. So the answer will be in a few minutes. Okay. Yeah, but it's 5 minutes, and then we will continue next time. Okay. Sorry, guys. So 5 minutes I will talk about. So great. So actually, I don't want to focus on the properties of GPU. You can read it by yourself. Let's focusing on CUDA programming definitions. So we have the number of blocks. Each block actually have their index, and each block have thread with their indexes. Okay, so for example, thread block number 0 have this have thread with index from 0 to 7, okay? And thread number block 1 have indexes from 0 to 1. So it's actually like your scope. So first you have block number, and then you have thread number. So you have index block 0 and thread index 1. It's like block 0, thread 1. So you have here block 0, block 1, thread 1, okay? So it's actually how we can distinguish between distinguish between the threads. Okay, so and each thread makes some operations. Okay, so we define our kernel function. Okay, and on kernel is executed at a time then control returns to CPU. So it's actually when we finished to compute. When we finish to compute our actually multiplication of array or something or other tasks, then we need to synchronize it. Okay, we need to understand that we finished because each of execution was in parallel. So you need some barrier. Yeah, you need to understand when it finished. So you have synchronization. Actually, synchronization using sync threads or making synchronization on the function is one of the one of the operations that actually a little bit harm to our performance. Yeah, because if we have some collision in some collisions between the threads, it's actually we need to wait until we finished. Then we understand. Then we know that we finished to do the operation because you need to do it manually. You have no other control. You need some control to understand when you actually finished to do the operation. So you do it by operation that it's synchronizing. Okay, great. So our execution rules. So all threads in grid execute the same kernel function. As I told you before, you can do only one. You can do all sets during the same kernel function. A grid is actually some 2D array of blocks, and each block is actually in a grid have same dimension. Okay, so total size of block or number of threads per each block depends on your GPU. And in the modern GPU, it's 1024 threads per block. Okay, great. So the definition of grid dim is dimension of our grid, and we can using the variable that contains this dimension. Block IDX is actually our index of our block. Thread IDX is index of our thread, and block dim and block ID. It's block dim. The variable continues dimension of the block. What the size of the block? How many threads there? Okay, great. So this is actually our this is the function that help us to do a CUDA program. Okay.
We can, for example, run two operations on the GPU.
What?
At the same time.
Two operations? No, you're talking about can you execute two kernels on GPU? Yes, you can execute two kernel functions on. If you have enough grids, you can use one grid for some kernel and the other grid to other kernel.
You can have multiple grids.
Of course, yeah. This is actually. Its name's multi-streaming GPU operation. I'm not. We will talk. I think that we will talk about it next week. It's more advanced topic, but you can create separate kernel, two or more than one threads. Of course, you need to more than one kernel. Of course, you need to sync between them. And it's actually why it's not so good, because synchronization, as I said before, it's harm to your performance. You prefer not to synchronize things in GPU. So, great guys, we finished for today.